All right, recall from our previous sections that linear means you have degree 1, quadratic means degree 2. So then in this section, we're talking about higher degrees. So cubic, like x cubed, degree 3. Quartic, like quarter, is 1/4. So quar means 4. This one's degree 4. And then just some general terminology. So term, if I have something like 5x squared plus 3x plus 2, each piece between the addition is the term. So the terms are separated by addition and subtraction. And then factor are the pieces that you multiply together. So pieces of multiplication. So that's like 5 times 3 are the factors of 15. 5 and 3 are factors. Whereas the product is the result of multiplication. So 15 would be the product. Okay, and then a new terminology, multiplicity, like multiple, is when I have a multiple of the same factor, we would say it has a multiplicity. So if I have f of x equals x cubed, because this is the same factor 3 times, it would have a multiplicity of 3. So a factor that repeats has multiplicity equal to its degree. In example 1, we're looking at transformations. So looking at part A, the first transformation order of operation that I want to do is the +1, so it moves to the left by 1. Second transformation is the 4, so I'm taking my y value times 4. X cubed, remember, is this shape, which means I'm taking the point at 0, 0, 1, 1, and -1, -1, and I'm transforming those points. So I go 1 over, multiply the y times 4 is 0. And then from here, 1 over multiply the y times 4 is 4. Here, 1 over multiply the y times 4 is -4. And so I have my new graph. And then to find the initial value is f of 0. So to find f of 0, I substitute 0. F of 0 is 4 times 1 cubed, which is 4. For part B, we're doing the same thing. My first transformation is to the right by 2. Next, I reflect over the x-axis, and then I go up 5. X to the 4th is this shape, so 0, 0, 1, 1, -1, 1. Starting with 0, 0, go to the right by 2, reflect, and then go up by 5. And then I go 1, 1, over 2, reflect, up by 5, 2, 4, 5. Same for my last point, over 2, reflect, up by 5. And this will be my graph. To find f of 0, I substitute 0 in. So I have negative of -2 to the 4th plus 5. 2 to the 4th, 2, 4, 16. So this is -16 plus 5 is -11. All right, in example 2, we're looking at the same graphs that we just did. So same transformation, same shape and everything as example 1. F of 0 we already found was 4 here and -11 here. And we can just copy over the graphs that we had before. Here and 2, 5, like this. Okay, now f of x equals 0. This means when y is 0. Y is 0 on the x-axis, so I'm looking for my x-intercept. So I have two ways to do this. The first way is to look at my graph and say this has an x-intercept of 1, x equals 1. The second way is if I actually let h of x become 0. So 0 equals negative x minus 2 to the fourth plus 5, and I want the x value. So I'm going to show you this work on the side here. 0 equals negative x minus 2 to the fourth plus 5. I want to get x by itself, so I'm going to subtract the 5. Minus 5 is negative x minus 2 to the fourth. Divide by negative 1 to get rid of those leading negatives. 5 is x minus 2 to the fourth. Now I want x, it's stuck in here, so I need to take the fourth root. Anytime I take an even root, I need the plus or minus. So I have plus or minus the fourth root of 5 equals x minus 2 plus 2 plus 2. X equals 2 plus or minus the fourth root of 5. X equals 2 plus or minus the fourth root of 5. Notice we should have two roots here because our graph intersects the x-axis twice. Okay? And then looking for maxes and mins, a max is where our graph goes from increasing to decreasing. This graph is always increasing, so I have no maximums. Since it's also always increasing, that means there's nowhere that it goes from decreasing to increasing, so we have no minimums. This graph, we do have a place where it goes from increasing to decreasing at 2, 5, the vertex. And there's nowhere that it goes from decreasing to increasing, so no minimums. Okay? To tell if these graphs are odd or even, we're looking at the symmetry. So in the first graph, can I fold it over the y-axis? No. Can I rotate it 180 degrees? No. That means it is neither. Even though it has the shape of an odd function, because it's been shifted over, it no longer has that perfect odd symmetry. Same for part B. It has the shape of an even symmetry, but because it's been shifted over, now it has neither symmetry. That's not saying the graph doesn't have symmetry, it's just not odd or even symmetry because those are very specific. The theorem at the bottom here just tells us that if I have a function, I can always identify its degree, and it can switch directions at most n minus 1 times. So if I have a degree 5 polynomial, it can switch direction 4 times. If I have a degree 3 polynomial, it can just switch directions 2 times. And what that means is, let's say I have degree 7, it starts one way, it switches 1, 2, 3, 4, 5, 6 times at most. Okay, it could have only 2 switches, it could have 3 switches or 4 switches, but it has to have at most 6 switches. All right, the overall shape of functions, if we have an even degree, the ends go the same way, okay, like x squared. So if I have a positive coefficient, they both point up. If I have a negative coefficient, they both point down. Now this is end behavior, so I'm not talking about what's happening in the middle. It could still switch directions in the middle. For an odd degree, I have something like x cubed. For a negative coefficient, this flips. So we have something like this. Okay, and how we can write that is that as x increases, so as we go to the right, x is going up. So I can say as x increases towards infinity, y also increases towards infinity. And we have limit notation that can help us write this as well. So when I'm looking at a limit, I can look at the leading term and I can say positive coefficient degree 3 is odd. So my graph will look like this as my x's go towards infinity. So the limit as x approaches infinity, my y's are also going to infinity. So g of x goes to infinity. And then for the other arm of the graph, the limit as x approaches negative infinity, so now it's as I'm going to the left, my y is going down, so g of x is going to negative infinity. If I have 2x to the fourth, so positive, x to the fourth is even, looks something like this. As I go to the right, as x is going towards infinity, my y's also go towards infinity. So the limit, as x gets bigger, my y's also get bigger. As x gets bigger, y gets bigger. And then we can say the limit as x approaches negative infinity. As my x's get smaller, so as I go to the left of my graph, my y's go to infinity, so my y's also go towards infinity. This should be f of x instead of g of x. All right, Next, we're going to look at finding the zeros or the x-intercepts of a function. So reminder, the zeros are also called roots or solutions or x-intercepts. Okay, so when I'm looking for the zeros, the roots, the solutions, the x-intercepts, I'm looking for the same thing. I'm looking for when my y value is 0, what is my x value? So to find the zeros algebraically, I want to set my y equal to 0, and then I need to solve for x, and in order to do that, I need to factor. So here I have a greatest common factor of x that I can take out. Here, x squared minus x minus 6. And then I need to factor the quadratic part of the function here. So I have 0 equals x times something factored. I have x. I need numbers that multiply to 6 and add to 1. So I have 3 and 2. It's a negative, so the 3 is negative and the 2 is positive. So what we can do here is use the 0 factor property, and I find it helpful to put my x in parentheses as well so we don't forget it. So my values of x can be 0, 3, and negative 2. In part B, we're doing the same thing. 0 equals x cubed plus 3x squared plus 3x plus 1. But this time we can try factoring by grouping, which notice the coefficients 1, 3, 3, 1. It won't work because my coefficients are not multiples of each other. However, that pattern 1, 3, 3, 1 should sound familiar. It comes from our binomial theorem, remember in chapter 9. So we can use that binomial theorem to know that this is a perfect power. And I can look at my first term, which is x cubed, my last term, which is 1, and my coefficient, which is 3, tells me it's to the third power, to remember that this is the same as x plus 1 cubed. So what this tells me is that x has to be negative 1 for f of x to be 0. And also, we can say that this has a multiplicity of 3 because it's the same factor that we've now seen 3 times. Okay, so multiplicity, remember, is the power of the factor that's repeated. When multiplicity is odd, the graph passes through the 0. When multiplicity is even, the graph bounces off of that 0. So think about x squared kind of bounces, x cubed goes through. Okay, so in example 6, we have f of x. I have it already factored, so I know that my zeros are at 3 and negative 2. And we can say that x is 3 with a multiplicity of 3, which means it will go through the graph at x equals 3, through the x-axis. And we also know that x can be negative 2 with a multiplicity of 2, which means the graph bounces off of the x-axis at 2, or at negative 2. So if I were to graph this, the general shape, if I distribute all this out, is x to the 5th. So it looks something like this. I know the end behavior based off of that. I know that 1, 2, 3, and 1, 2 are my intercepts at 3 and negative 2. I know it goes through 3, and it bounces off of negative 2. So this is the shape of my graph without having to use my calculator or find exact points other than the zeros. All right, on the next page we have a really powerful theorem. It's called the intermediate value theorem, or IVT. It's probably one of the most useful and popular theorems in pre-calculus and calculus. And it says that if I have 2 points, A and B, and their results, so f of A and f of B, have opposite signs, one of them is positive and one of them is negative, that means that somewhere between A and B, I have a 0. So for example, here I have A and B. F of A is negative, f of B is positive, and since we go from negative to positive, we know that there has to be a 0 in between there. Between negative and positive will always be a 0. If my graph was decreasing, I could have gone from positive to negative, but there would still have to be a 0. Okay, so using the intermediate value theorem, I want you in your own words to try example 7. And then for example 8, you're using your calculator. Remember, we found zeros on our calculator in chapter 1. We're doing the same thing, but now we have a polynomial function, and because these are non-integers, we can't factor, so we need to graph this and see where the zeros are, calculate them on your calculator, and then list them here. All right, pause the video while you do example 7 and 8, and then resume the video when you're ready to check your answer for example 8. So upon graphing this, we find that the zeros are when x equals negative 3.1, 0.5, 1.13, and 1.37. All right, lastly, we want to see how do we apply this, how do we use it? Well, we can use it to model things like finding the volume of a box, like in this example, or we can use it a lot of times in economics or physics, chemistry, biology, computer science. We can also use this in analyzing language and language fluency and development of language. So this is one of those areas that's applicable in a lot of ways. We're going to apply it in terms of finding the volume of a box. So we need a box that has a volume of 484 cubic inches. We are cutting squares out of the corners of the boxes. Now, because I'm cutting the square here out of a 20-inch side of a box, I know x can't be bigger than 10. X has to be smaller than 10. Otherwise, I can't cut it from this side of the box, right? I would also have no volume if x was 10. So to find the volume of this box, volume is length times width times height. Okay, so the length here is 20 minus 2x. Okay, we'll say the width here is 25 minus 2x, one from the top, one from the bottom. And then finally the height is x, because when I fold this box up, it will have a height of x. Okay, so taking this, I want it to equal 484. So we have a couple options. We can graph y1 equals 484, y2 equals 20 minus 2x times 25 minus 2x times x, and find where they intersect. Or we can do y1 is 20 minus 2x times 25 minus 2x times x minus 484. Okay, and find out the zeros or the intersect. Okay, so go ahead and pause the video now while you try that with your calculator. And remember, we need an x value that's less than 10 for this to make sense. All right, once you've tried this, to confirm your answer, you should have x equals two different values. There's two values that will give you this volume of 484 cubic inches, and that is a 1.22 inch cut, so 1.22 inches by 1.22 inches, or you can make a 6.87 inch cut. So there's two different sizes that you can cut out from the corner of these boxes. All right, now take a moment to do your summary, your 1 to 2 sentence summary of this lesson.